Hi everybody, so we're going to look at the scales of the universe, see how well you did and how they compare to what I put. These are your notes, so don't worry about whether you got things right or wrong, and I'm going to point out a few things that I want us to all agree upon for a later exercise. Then we're going to talk about the same thing for masses. What is the most massive thing in the universe, and what's its value, and what's the least massive, and do a chart like that. That I'm going to just give you, and you're just going to do some quick little exercises with that. Rather than you research that. Okay, so what I want you to highlights that I want to make sure we're clear on is the nuclear. The nucleus I want us to settle on 10 to the negative 15th. You might have had negative 14th, negative 16th, something like that, but just put negative 15th for later reference. The same with atomic. These are two important scales. So the atoms, most atoms are in the order of 10 to the negative 10th. Hydrogen, you could argue, is 10 to the negative 11th, but we're going to go with the majority, so negative 10th. Another important one is the size of the Earth. I think we agree upon that that's 10 to the 6th meters, so the diameter of the Earth is roughly 1,000,000 meters across, whereas a large planet like Jupiter is 100 million meters across. So that's pretty interesting. So you would need 100 Earths end to end to go across Jupiter. That's how you can use these numbers, and that's pretty cool. In fact, if you want to do volume, volume goes by the cube of the radius or diameter. So the cube of that is 10 to the 18th. You don't have to do this. The cube of this is 10 to the 24th. So if you divide 10 to the 24th by 10 to the 18th, you get 10 to the 6th. That means you could fit roughly 1,000,000 Earths inside Jupiter. Unbelievable. Okay. Another number that I want to make sure that we are in agreement on is the extent of our solar system. So our solar system is huge because this Oort cloud goes well past the orbit of Pluto. If we just restricted to Pluto's orbit, that would probably drop by an order of magnitude, but we're going to go with 10 to the 16th. The size of a Milky Way galaxy. So our Milky Way galaxy, if you don't understand, is kind of like this. This is like a bunch of stars that go out like that, and in those stars, in this galaxy, this is a big cluster, are gazillions of stars. Okay, and our sun, if you don't already know, is one star way out here in the suburbs, somewhere in the arms of the galaxies. So there are multiple galaxies within the universe, and in each galaxy are many, many, many stars. And so what you found in the notes is that, or in the website, is if you go across that, it's about 10 to the 21 meters. All right, that's a number I can't even really comprehend, but it is known. The last one that I want to make sure we agree upon is how big is our observable universe, 10 to the 26th. If I have time, I'll show you a video on what it means by observable as opposed to the whole universe. So the idea of our own universe is pretty complicated and very fascinating. Okay, so if you did the problems, you did the maths, then how many orders of magnitude as physicists do we have to understand? It's roughly 44. You might have had a slightly different number depending on what you had for universe and quarks above. But this idea. So we have to understand a 1 followed by 44 zeros. That is our universe is encompassed by that. Now that number is not super significant in and of itself, but I want you to understand it's not infinite. It's not like there's an infinite distance out there going to the largest and to the smallest. There seems to be finite distances, and we as physicists have figured it out over many, many years. If you look at this column right here, you will see if we start in the middle, we've known these distances forever, and then as we go this way or this way, they got later and later and later. So we just figured out this distance actually within the last 10, 20 years. And this we've just figured out within the last 10 or 20 years. So there's an interesting parallel between the scales on either end, either extreme, and when we discovered them. And we're constantly probing, but we're pretty confident we have covered as much as we can. All right, now in terms of laying things end to end, you should have gotten around 10 to the 10th, maybe 10 to the 9th, 10 to the 11th, depending on what you had up there. And make sure you show your work how you got that, because that's what I'm going to look for, not just having the answer. And the number of cells to laid end to end to make up one human is 10 to the 6th, 1,000,000. Now, that doesn't mean our body is made up of 1,000,000 cells. We know it's much more than that, on the order of trillions. That's to fill our body, not necessarily to go end to end. Okay, so let's look at this. What pattern do you notice? I already talked about that pattern, that the more extremes took longer or are more recent. And why is that? Well, that's simple. Technology. Okay, it takes a lot of amazing technology to probe the vast distances, like the Hubble Space Telescope for those distances. And for the tiniest distance, we need these things called particle colliders, okay, which are the most powerful machines we've ever built. All right, now let's turn our attention to mass. So the universe is occupied with massive objects, large objects, tiny objects. So they come in scales, kind of like distances, and I want you to fill this out. Okay, and I want you to contemplate this. This might seem incredible, but we know these values fairly well. Our universe, which is made up of all the stars and planets and etc., has a total mass of around 10 to the 52 kilograms. Not 10 to the 51, not 10 to the 53, 10 to the 52. Okay, and I'm not going to talk about other exotic things like dark matter or dark energy. I'm not sure if that figures into this, but this is stuff that we can observe. The Milky Way galaxy, which our solar system is a part of, is 10 to the 41 kilograms. Inside, we know at the center of most galaxies and our own is something called a supermassive black hole. 10 to the 36 kilograms. That's unbelievable. So that's roughly 1/50th, or excuse me, 100,000th the mass of the entire galaxy. Our sun is 10 to the 30th kilograms. That's an important number. And the Earth is 10 to the 24th kilograms. Two very important numbers in physics. And we're going to talk about how we know that. I went on Google asked how much water, oceans, lakes, rivers, etc., what is the mass? And as best as I could figure, it's 10 to the 12th. Notice that that's 1 trillion times less than the mass of the old Earth. So the Earth, that kind of makes sense. Even though the Earth is covered with 70% water, it doesn't take up 70% of the volume. It takes up much less than that. All right, on the oceans, you might find a ship that's 100 million kilograms, an automobile 10,000, a human, you should know this. You can be asked that on a test, and to be able to estimate is about 100 kilograms. A cell phone is roughly 1 kilogram. Actually, I should change this. It should not be a 1, it should be a 0. Okay, so if a cell phone is roughly 1 kilogram, then that's 10 to the 0th. A drop of water, -4. So it's a 10,000th. A grain of sand is less than that. Now, sand varies, but we'll just stick with that. Virus, coronavirus, obviously affecting our lives profoundly in the last 6 months and into the future, is -17th. Where, now what is that? That's made up of molecules in that. And molecules are made up of atoms. Atoms are made up of protons and neutrons and electrons. And the proton, which is the heavy part of an atom, -27 kilograms. Tiny. And then the smallest particle that matters for us right now is the electron. And so we're going to treat this as the tiniest mass in nature, even though that's not quite true. There's something called the neutrino that has less mass, but we're not going to worry about that right now. Okay, so we can do some problems right here involving these numbers, and I want you to try those on your own, and then either I'll post answers online or talk about it in class depending on the timing. Okay, one thing I want you to think about, and I'm going to build a lesson around this, a short lesson, is how do we know these values? Okay, especially these right here. We can't measure them directly. How on earth do we know that the Earth has a mass of 6 times 10 to the 24th kilograms? We can't set it on a scale. Even if there was a scale big enough, that wouldn't work. So how do we do that? That's a really, really interesting and cool question. And that's really getting to the heart of what we're going to do in this class in physics. I'll give you the teaser or the spoiler for the answer. How we know this is because we can make other measurements about the Earth and use physical principles to put those measurements together to come up with a calculation that says, in order to explain these measurements, the Earth's mass must be this. And we pretty much do the same thing with the sun, the universe, etc. It's a really, really cool idea. And in a very real sense, we do the same thing way down here. We don't measure them directly, we do it indirectly. In fact, there is a lab I hope us to do, or as a demonstration, where we can determine this mass by watching electrons behave in the presence of a magnetic field, make measurements of that magnetic field and other parameters, and we can infer based on the physics that explains the phenomenon, see the mass electron must be that value. And that is pretty kick-ass. Okay, so as always, if you have questions, make sure you ask one way or another.